Okay, here we go. Pandemic lecture. I don't know how many we're in now. 5 maybe. Here we go. This is our Canvas site that I'm setting up, and got a lot going on now. A couple things I wanted to point out was the discussion section. Post and read questions here. So if you have a question for me, instead of emailing me, post it here in the discussion board, and then I'll answer it, and everyone can see it. Know that when you post me a question, everyone can see it. So if it's a private question, you can email me. And also read the answers. So if you go check those out, like chapter 15 and 13, 14, and 15 are up right now, you can see what other people are asking and my answers. It's real helpful. And then turn in stuff there, the assignments. If you click on the assignments link, you'll see like folders for homeworks, labs, extra credit. So turn everything in there, and I'll grade it in there. This is pretty cool. This is the benzene's aromaticity. You can see it's got resonance where, see, I don't have a pi bond on, I have a pi bond on the bottom here, but not there, so you can see there's resonance, and there's the resonance hybrid. A lot of times people get lazy, they don't draw the dots, they just draw a circle. And if you rotate it out of the plane of the page like that, you can see this is coming out at you. That's what this is looking like, and you can see this is actually the lowest energy pi molecular orbital, all in phase orbitals. So it looks kind of like that. It's interesting stuff. We're going to talk more about that. So our schedule, we will have the exam next week. It won't be over chapters 13 through 18-ish. It'll be over chapter 12. The very end of 12, we didn't actually have dihydroxylation or ozonolysis on the last exam. So I'll throw that on this exam. And sorry, Morgan, you asked me today, is ozonolysis going to be on this next exam? And I'm like, I don't think so, but I think it will now. But I won't go too crazy with it. And then up through chapter 16, we probably won't get through all of it for that exam. I'll let you know. All right, so now I want to show you predicting the energy levels of an aromatic ring. The pi molecular orbitals are not the, we're going to predict the energy level, the number of pi molecular orbitals and their relative energies, not their orbital phases though. I'll show you what that means. So first thing you do is you draw out your aromatic ring with the pointy end down. So you can see right here, this guy, it's got a flat end down, not a pointy end down. So let me rotate that around. So I'm going to slowly rotate it around. Boom, there we go. And now the pointy end is down, or one of the pointy ends. And then at each carbon in the ring, you have an energy level of your molecular orbital diagram. It's a pretty interesting little trick, huh? So the benzene has 6 p orbitals, so we expect 6 molecular orbitals, and that's how they'll arrange themselves, like that. There'll be a lowest energy molecular orbital. That's the all in phase, no nodes. And then these ones are going to be different. The phasings, we won't actually learn how to derive those. I'll just show you them. But it's nice for you to see how you can at least figure out that. And I'll show you why that's good. Because now you can fill in your pi molecular orbitals. So we have a total of 6, right? So there's 1, 2 in the lowest energy. And then we go 3, 4. You fill in half fill, same energy level. Then you complete them. And that's 6. And so this trick doesn't actually give you the, just want to repeat the p orbitals, what their phases are and stuff. But on the next slide, I'm going to go ahead and show you the answer for those. So here it is. So we have 6 p atomic orbitals, so we should get 6 molecular orbitals, and that's what they look like. And we have 6 pi bonding electrons, like we saw on the last page. So you can see the lowest energy molecular orbital, no nodes, all in phase. Here's a cool like graphical image of it. The blue and red phases versus dark and light. And then you'll see on this next level, energy level, you have a node right there, huh? Those two are out of phase. And a node right there. So you have 2 nodes. How many nodes does this guy have? I'd say this guy has no nodes because that's in phase, and there's actually no contribution of this p orbital to the pi bonding. It's interesting, huh? And then this one, how many nodes do you see? I see 1 there, 2 nodes. On this guy, how many nodes? No node. Oh, there's a node. Oh, there's a node. Any node? Nope. There's a node. There's a node. So 4 nodes. This top guy, like we've seen in the linear pi molecular orbital diagrams, every bond is a node. That's the real high energy. So I haven't taught you how to get these orbital phases, but It's neat to see, right? And you can see how they look with their cool red and blue. You see all the nodes. You see the nodes through these guys and those guys. It's kind of cool, huh? Looks like hot dogs, kind of. All right, and then so what do we have here? That's a bonding interaction. So I got a bonding interaction there because they're in phase. And if you look around the ring, they're all bonding interactions. So on this one, I've got one bonding interaction, 2, 3, 4. 4 bonding, 2 nodes. This guy, 1, 2 bonding. Up here, none on this one. This one's got a bonding interaction, another bonding interaction. And that one, it's getting late. That one's got no bonding interaction. So what does this all mean? Why am I mentioning this? Because we can calculate a bond order now. So this bond order, I'm going to use BO to represent that. So BO has of 6. This guy has a bond order of 6, lowest energy, because it has 6 bonding interactions. Whereas these guys have a bond order of 2, because they have 4 bonding. Well, this one has 4 bonding and 2 anti-bonding, so 4 minus 2, 2. This one also a bond order of 2 because it has 2 bonding and no anti-bonding, so 2 minus 0. Now this one has got 2 anti-bonding only, so it's a bond order of negative 2. You can see how having a negative bond order makes you an anti-bonding orbital, higher in energy. And this one's got 2 bonding, 4 anti-bonding, so 2 minus 4, minus 2 as well. That's why they're the same energy. Up here, what's this one? 1, 2, 3, 4, 5, 6. 0 minus 6, bond order negative 6. Okay, so what's with all that mumbo jumbo? Well, it actually is used to explain the why things that are aromatic are lower in energy and why the anti-aromatics are higher in energy. So it turns out this one, as I said on the last slide, has a bond order of 6, bond order 2, bond order negative 2, bond order negative 6. So in a benzene, which is aromatic, all the bonding orbitals are filled. None of these destabilizing anti-bonding orbitals. So this is overall bonding, overall anti-bonding. So you can see benzene's real stable. And then when you go to a potentially anti-aromatic example, so this one's potentially anti-aromatic because it has the 4 pi electrons, and that falls into the 4n rule. So let's see how it looks. Oh, I'm going to do just like I did with the benzene. I'm going to tilt it to put a pointy end down. There we go. And then I'll draw in where the orbitals would be. And so they'd look like this. It's got 5 p orbitals, p atomic orbitals, 5 molecular orbitals. And how many electrons? 2, 4. So I go 1, 2, 3, 4. That's how you fill it. And those, it turns out, you fill each one half full. That's the lowest energy. Filling, I forget the term. So this down here, this guy is a bonding orbital, but that one, those ones are all anti-bonding. I don't have the p orbital phases for you, but they have more nodes than they do, or they just have an overall bond order that's negative. So when you have a situation like this, the anti-bonding orbitals get filled, and that's what makes it so high in energy. So a little background on that. Okay, and now I'm going to talk about the NMR of benzene, because I didn't really talk about it last time, I forgot. You already know the results of this, but I'll explain a little bit. And a little bit of review. So let's look at this hydrogen here. It has electrons around it. When the magnetic field of the NMR interacts with these electrons, they can rotate in a way to create their own little magnetic field that can oppose the NMR. And when that happens, they're shielding the nucleus of that hydrogen. So the hydrogen's nucleus feels the NMR's magnet minus a little bit from the shielding. So let's look at an example. I've got this alkane here, might show up at 0.9 parts per million, and then I've got an alpha to an oxygen, 3.8 parts per million. So let's look at the magnetic field of the NMR. That's very strong. And the magnetic field of the shielding from the electrons around the nucleus of the hydrogen, they'll subtract a little bit, so you'll have something like this. That's what this guy will, the electrons inside of these hydrogens will feel. And then I've got the same NMR, but now the hydrogens here, they have less electrons around them because the oxygen is withdrawing those electrons, de-shielding it. So it gets less shielding, less electrons to shield the nucleus, so it'll feel more of a magnetic field, and that's why it's at 3.8. Right? That one's see. Nice, right? Okay, so now back to benzene. So benzene is really interesting because of its pi bonding above and below the perpendicular to the plane of the atoms. And so that green arrow is to represent the NMR's magnetic field. And the pi electrons are induced to rotate by the NMR's magnetic field. So the hydrogen here has its own electrons. That's the one we were just looking at on the last slide. They oppose the NMR to shield. But while they're doing that, the pi electrons are also having an effect. They start spinning around and they create these cool magnetic field lines that circle through the ring, up the outside, and then back down the center of the ring, and up the outside and down the center. It's interesting, huh? So yeah, the pi electrons rotate, creates a pi electron rotation creates its own magnetic field. So now this hydrogen is influenced by the NMR's magnetic field, its hydrogen atom electrons shielding, and also these pi electrons creating a magnetic field. And here on the outside of the ring, the magnetic field from the pi bonding is actually adding to the magnetic field of the machine, of the NMR. So on the outside of the ring, you're actually deshielded by the pi. So the hydrogen's 1s orbital electrons, they're shielding a little bit, but then these pi bonding electrons are causing deshielding. On the inside of the ring, there's actually shielding going on. The inside of the ring's magnetic field subtracts the NMR and shields. So in the inside, there's less of a magnetic field felt, but there's no atoms in there. There's not a hydrogen or anything in there, so you don't really see the effects of that for benzene and NMR. But let's compare now regular alkene here. Where do its hydrogens show up in a proton NMR? About 5 to 6. Yeah, this would be a 4-hydrogen singlet, about 5.3 parts per million. On benzene, it would have a 6-hydrogen singlet, and it shows up at about 7.3 parts per million. And why did it show up more downfield than the regular alkene? Because the hydrogens sit outside of the ring, and the pi bonding causes them to be deshielded. So, okay, that's pretty cool, right? We're explaining why we memorize that value of benzenes around 7 and regular alkenes unconjugated are around 5.3. Now let's see if we can look at an example where we look in the middle of the ring. Okay, so there's this 18 aniline compound. There's a lot of anilines. Actually, benzene can be referred to as a 6-aniline because it has 6 CHs around the ring. 18 aniline has 18 carbon hydrogens around the ring. So here's an example. Looks like almost like a Carl's Jr. superstar gone crazy or something. I don't know. So this molecule right here, let's check it out. Is it aromatic? Can it be a flat ring? I think so. Can it have sp2 atoms all the way around the ring? It does. And how many pi bonding electrons does it have? So I'm going to start my cursor off right here, and then I'll count around clockwise. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 pi bonds. So that's 18 pi electrons. That's a lot. Is that going to be aromatic? I know 6 is because benzene, but let's work the formula out. So the formula to generate a series to see what's aromatic and what's not is 4n plus 2, and n has to equal 0, 1, 2, 3. So, this stupid thing. The n equals 0, you get 2. When n equals 1, you get 4. When n equals 3, 0, you get 2, 1, 4, blah, blah, blah. You work it all out. When n equals 4, you get 18. So, bam, that guy can be aromatic. Isn't that cool? Big old monster of a molecule, huh? And this was a big discovery, actually. When they made this molecule and studied it, they really supported a lot of the theory of aromaticity. All right, so here we go. I'm drawing out the resonance hybrid of this right here. And if we look at it, you'll see there's outer hydrogens that are all equivalent. And then there's they would be a 12-hydrogen triplet. You'd predict, right? Because it has a neighbor here, and then it has a neighbor on the inside that's trans from it. So it's going to get different coupling constants to the neighbor that's trans and the neighbor that's cis. So I'm going to say a 12-hydrogen triplet. And where do you think that shows up? it's on the outside of an aromatic ring. If you remember, on the outside of an aromatic ring, you get deshielded. The pi bonding adds to the magnetic field of the NMR. So where's that one going to show up? 12 hydrogen triplet, 9.5. Awesome, huh? So benzene deshields their hydrogens down to like 7.5 or so. But when you have more pi bonding around a bigger ring, it gets deshielded even more to 9.5. Okay, now even cooler than that, so outside the ring is deshielded. Even cooler than that is the inside of the ring. The inside of the ring here, these guys, they're a 6 hydrogen triplet. I'm saying that because it has a trans coupling and another trans coupling, and those are equivalent, so I think those are equivalent neighbors. So yeah. So, oh yeah, can we get over to these guys? 1, 2, 3, 4. Oh, crap. 1, 2, 3, 4. Oh, yep. I should have 1, 2, 3. I should have a pentet there. Oh, let's fix it. Dope. My bad. Come on. There we go. Pentet. Oh, of course. There we go. Oh, I gave away the answer. Let me go back to this one too. Why not? That was bugging me. Is that bugging you guys? Okay. So back to present mode. Okay, 6 hydrogen pentet. And now this is on the inside of the ring, something benzene doesn't have, hydrogens in the inside. And they show up at negative 2.9 parts per million. Pretty awesome, huh? So it goes along with the theory that the inside ring is shielded because of the cool magnetic field lines of pi bonding. And there's another interesting thing about this. The average carbon-carbon bond, single bond, if it has no pi bonding, is about 154 picometers. Picometers are tiny, right? They're 10 to the minus 12 meters. And the average carbon-carbon double bond is shorter, 134 picometers. So 134 for a full double bond, 154 for a full single bond. What are these guys? That one's 141. It's in between the two. That makes sense, huh? It's not a full double bond. It's not a full single bond. It's kind of in between. Interesting thing about this, though, the bonds are not equivalent. Like these inner ones are a little shorter than these outer ones. So this is 141. That's 141. That's 141. But then these two are 139. I don't know why. You can see they're colored according to, on this molecule too. The blue ones are 139, and all the red are 141. I'm not sure why that is, but they both still fall in between 154 and 139, right? So you can see there's partial pi bonding. Okay, and well, I could tell you a little bit more. So we talk about aromaticity, and benzene has like perfect aromaticity. Other things you could say are like kind of aromatic, partially aromatic. This one is kind of partially aromatic. There's other like instead of the 18 aniline, the 14 aniline, it's not very aromatic because the hydrogens in the middle get too crowded because it's a smaller ring and they distort it out of planarity. It's not planar. So anyways, well, you can go on forever with this stuff. This is another cool one. This molecule, is it aromatic? Let's see. It has 14 pi electrons. 2, 4, 6, 8, 10, 12, 14. Does that fall into the formula? Yep. It could be aromatic. Oh, I did say the 14 aniline on the last slide is not aromatic, but this one's not a 14 aniline. This molecule is a little different because it has 14 aniline wouldn't have any of these carbons in the middle, but since we have these, they're kind of holding that ring flat, these middle atoms, and so this is pretty cool. These methyls are in the middle of the benzene ring, and they get deshielded all the way to negative 4.23 relative to TMS. Pretty cool, huh? So a lot of deshielding in the middle of the ring, and then the outer part of the ring gets up almost to 9, huh? Because it's on the outside of the ring. It's deshielded. Yeah, deshielding on the outside, shielding on the inside. Okay, and then before we get going on the lecture on the whiteboard, I put up lab data finally. Today I finally got the distillation data up, and I'll keep adding more to that. I'll do the banana oil next, I think. Yeah. For those of you who didn't get all the banana oil data, I'll put that up for you. So as I said before, you'll take whatever data you already have. If you collected any data, use that. But then anything you're missing, go to my lab guide and you'll find it. It's right here under lab guides. Where before I just had these 4 documents, now I have the data for distillation, and I'll be adding data for banana oil and aldehyde enigma, and then I'll be adding data and like experimental little pictures and videos for the other experiments we didn't get to even start. And then for this one, for those of you who need to do the use this data, I changed up the questions a little bit, and for the report questions and commands, use my new stuff it's in here when you get there, and it explains it in there. There's one other thing I wanted to touch on from back in chapter 14. I just noticed it when I was going through my stuff. I was going to tell you a little bit about UV vis spectroscopy. We don't actually do much of that in lab, but I still think it's a good one to mention. It's used a lot in science. So like other spectroscopy, you have a light source. Usually you'll filter that out, and then you'll have a certain intensity of light coming into your sample, and your sample might absorb some of that, and then only a fraction of the initial intensity comes through, and the detector detects what comes through and then knows what didn't come through and can make a spectrum. So in which NMR uses radio waves for its light source. I think I said it already, huh? And oh my, I like the way it does that. NMR uses radio waves. What do you think uses microwave radiation? It's microwave spectroscopy. We haven't talked about that. What uses IR radiation? IR, infrared, right? Or infrared's IR spectroscopy. And ultraviolet visible radiation is used for UV vis spectroscopy. And you probably talked about this in general chem, how like the energy of a photon, Planck's constant times the frequency, and frequency can be expressed as the speed of light over the wavelength. And you know what? You can look at this and be like, we're not going to use it this semester, but well, we'll talk a little bit. We talked a little bit about this with our UV vis detector on our HPLC, huh? The absorption of light in an ultraviolet spectroscopy is equal to the molar absorptivity of the molecule, how much it absorbs that wavelength, the concentration of the sample, and the path length. Okay, so then I'm going to go back to linear conjugated pi bonding. So this one's the 135 hexatriene. So how many pi electrons does this guy have? 2, 4, 6. So let's fill it in. 2, 4, 6. When the right energy ultraviolet or visible light hits this, it'll promote one of the electrons up. So now our excited state will be the following. 2, 4, 6. And so now, instead of having a highest occupied molecular orbital here, lowest unoccupied molecular orbital here, now we have our singly occupied molecular orbital, our SOMO, and then a lowest unoccupied molecular orbital there. So that's what happens when the ultraviolet and visible light hits a molecule like this. It promotes an electron up a level. So why do I mention that? That's also how we see things. So when before I say how we see things, actually, so this is a UV vis spectrum, and you'll see it's opposite of IR. We show it as the higher up is a strong absorption, and the lowness is a weak absorption. We invert that in IR. So anyways, we got these different wavelengths. Visible light is around 400 to 800 nanometers. That's what we can see. So we can see this stuff. But ultraviolet's over here, the higher energy, shorter wavelength, and we can't see that. But other animals can. And this is a cool concept. The more conjugation a pi system has, the longer the wavelength of light it absorbs. So for instance, Does this have more conjugation than this, or which one of these two would you say has more? I would say that has more pi bonds, right? And even more. So this one, this is naphthalene. It's actually a white solid. We can't see, all light is reflected from it, and we aren't seeing it as any particular color. And it absorbs strongly in this region here, which is in the ultraviolet region, right? That's why we're not seeing it. Whereas this one's more conjugation, and its strong absorption is moving to longer wavelengths. And then this one, it's getting into 300, a strong absorption there. Can we see that? It's a little too short of a wavelength still to see a color. And then this particular molecule, this is called azulene. It has a strong absorption around 270 or so. Not quite. No, we need to get to like 400. So it's absorbing pretty strongly here, actually, though. So we do see it. It has a purple color to us because we can view. There's enough wavelengths that it absorbs there. All right, so you can see some more trends like this. So, like for example, is this molecule, does it have conjugated pi bonding? This one? Nope, no conjugation there. It's maximum absorption well into the, it's actually maybe below the UV. And then this one has some conjugation, and its absorption, maximum absorption is increasing about the same. Now we got a third pi bond. It went up again, huh? Now we got 4. It's getting into the visible light. And then let's look at this molecule here. We got a steroid, 355. And here's the azulene. This one, it appears to us blue-violet because it's got a lot of conjugation around the outside of it. And then I really like this one here. This is beta-carotene. This has a lot of conjugation, huh? It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pi bonds in conjugation, and those we can see them as an orange color. That's the orange color of carrots. So which of these do you think might have color to our eyes? Benzene or this guy? It's going to be that guy, right? Because more conjugation. There's beta-carotene. Okay, so this is really interesting. So beta-carotene, in our bodies, it reacts with oxygen, and we have enzymes that catalyze this reaction to create 2 of these molecules here. Where it has a cis alkene. This is cis and trans. What is the name? Oh, retinol. I don't know why the name's not shown. So this is cis retinol. So in our body, we create that molecule, and that's in our eye. When a photon of light hits this molecule, it can make this cis alkene go to trans. And when that occurs, it starts a neuro pathway to your brain saying, oh, we just absorbed this particular light color. And then your brain can create an image from that. So the cis to trans is the key. And that's it. It sends a signal from your eye to your brain. So it's alkenes going from cis to trans is why you can see what I'm drawing up here right now today. And this is the protein rhodopsin that's in your eye. And these are alpha helixes. Probably heard of those, the proteins, and the red area is the rhodopsin, this molecule here that's in the middle of the protein there. And then when it goes from cis to trans, it causes the protein to send a signal to your brain. Pretty cool, huh? I'm excited. I got the whiteboards nearly the same height now, which is nice. Propped it up on some charcoal and some dog food. And I got the better idea here, so hopefully this comes out better. And I think I got the glare down. So I've been doing problems like this one here on my office hours, and I got ones real similar to this, and I explain it in more detail too. I really go through it slow because I figure you got lots of time there. So if I were you, if you're at all confused about this question, look at the office hour videos and or the Google Slides. It'll help you get good at this. So which of these is a stronger acid? So first off, we got to ask ourselves as always, which is the most acidic proton? So for this one, I have a vinyl hydrogen, some allylic hydrogens. Vinyl, allylic, vinyl. The allylic's going to be the most acidic. So let's deprotonate that. So the water can deprotonate that possibly. We'll see. We'll analyze it, see if it makes sense. Okay, and same type of reaction can happen for this guy. Okay, so I gotta analyze these conjugate bases and see which one's the weakest base, the most stable, because whichever one's the weakest base, the most stable base, will have the strongest conjugate acid. So let's look at these. For this one, it will have a resonance we can draw. Put the negative charge on the nitrogen there, and another resonance structure. So every ring can get a negative charge. This one, it'll have 5 resonance structures. This is only 3 resonance structures. So when you look at that, you might think, oh, it's got more resonance, it's going to be more stable, it's going to be the weaker base, conjugate acid's going to be stronger. And that might be the case, but not always, because of aromaticity. Aromaticity can come along and contradict all this number of resonance stuff. So we have to first look at this and say, okay, are these possibly aromatic? So let's look at that. So the first one, to be aromatic, you have to be a flat ring. You have to, that could be a flat ring. You have to have sp2 atoms all the way around. That can be sp2. And you have to have a particular number of pi bonding electrons. So you have to have 4n plus 2 pi bonding electrons where n equals 0, or 1, or 8, 9, 10. It goes up by 4 every time. Okay, so how many pi bonding electrons does this have? Let's make sure we count these correctly. So this nitrogen here, if it's sp2 hybridized, it needs to have 3 sp2 orbitals with atoms or lone pairs to them. So it has a carbon over here, a carbon down there, and that lone pair has to go there in the sp2 orbital. So does that count towards pi bonding? No, it's not pi bonding. I went through this in the office hour a number of times, so if you want to check it out if this is a little bit unclear for you. And then this one down here, it has 1 hydrogen on there. And so that carbon is, if it's sp2, it would have a nitrogen here, a carbon here, a hydrogen there. So that lone pair then would go into the p orbital. So that lone pair is pi bonding. I will count those. So how many pi electrons does this have overall? 2 4 pi electrons if we go with this. So would we want to have 4 pi electrons? Does that make the molecule aromatic? No, it doesn't. Oh yeah, this means it could be anti-aromatic. So that's not good because it has the 4 n pi electrons where n equals 1, 4, 8, 12, 16. Not looking good. So this is going to be a very high energy base. It's not going to be very stable. Its conjugate acid is going to be very weak. And it's probably not going to be even anti-aromatic. My guess is it'll choose to do this. Put this carbon to be either this carbon, or actually it's probably going to put it on the nitrogen. It's more electronegative. Something like that, though. One of the atoms will be sp3 hybridized, thus avoiding being anti-aromatic. So this one is not aromatic. Let's look at the other one. Okay, is this one aromatic? So I've got to figure out where these lone pairs are going. There's a minus here. For this carbon, it is, if it's sp2 hybridized, it'll have a hydrogen over here, a carbon there, and the p orbital then that's perpendicular to the sp2 plane, it will have the lone pair. So yep, those count towards the pi electrons. And the nitrogen, it has to have 3 sp2 pi bonding orbitals, and then we'll fill those in, and you'll see, I'm going to double check on the glare here. It looks alright, I guess. It has a carbon here, and a lone pair there. So that lone pair is not in a p orbital. So this one does not count towards being aromatic, because that's sp2. So how many pi bonding electrons do I have for this molecule? I've got 2, 4, 6. 6 pi bonding electrons. Does that make me aromatic? Yes, it does. So this molecule is extra stable, lower in energy, and it will then result in the conjugate acid being stronger. So this is the stronger acid. And this one also had more resonance in its conjugate base, and it was aromatic, so it kind of the resonance idea and the aromaticity, they agreed, but they don't always agree. For instance, I worked out a problem like this one in the same type of question. You should try it out yourself. It's in the office hour work. This acid versus this acid. Look at it and see which one's more acidic and which one is conjugate based, whether it's aromatic or anti-aromatic or whatever, or neither. And then if it's how many resonance structures it has. See about that. These two molecules are the discussion of the extra credit assignment I gave you guys to the aromatic anions. Okay, let me try a different type of example like this. This is another type of problem that I worked out examples of in the office hours. So if you're confused by this example, you got more to look at that are worked out on video and posted on the Google Slides. So we're looking to see which reaction here we predict would be faster as an SN1 reaction. So let's start with the top one and do the mechanism. So we know for an SN1 reaction, the first step is normally just the leaving group leaving. If you have a good leaving group, which bromine's a good leaving group, so it just comes off on its own. That's the rate determining step. The unimolecular rate determining step, just one reactant molecule reacting unimolecular. We get a carbocation and the bromide. And now the methanol, is it a weak or a strong nucleophile? It's a weak nucleophile. So it wasn't going to react with the bromide before it came off, but once it comes off, this carbocation is an extremely strong electrophile. So they'll react because one of them is very strong. We'll initially get the methanol on there with the proton, and it just needs to be deprotonated. Giving us the final product. Okay, so what's the most important step to the rate of this reaction? The rate determining step. So what does that look like? Let's check it out. It's got the carbocation, and can it be aromatic? That's the big question. Can it be a flat ring? Yes. sp2 all the way around the ring? Yes. Number of pi bonding electrons? Just those two. Does that fall under the category of being aromatic? Let's see, 4n plus 2. When n equals 0, we get 4 times 0 plus 2. 2. Yep, this is aromatic. So that means it'll be much lower energy carbocation than you might expect. And if it's low in energy, then that means it's easier to form, and it should be a fast reaction. What about the other one? The other one would produce a carbocation like this. You could work out the full mechanism for this one. It's basically the same. And now, how many pi electrons does this have? It has 4 pi electrons. Is that aromatic? No, that's anti-aromatic. Possibly. So that means this is a very high energy carbocation. It's going to be harder to form. It's going to be slower to form. So this is definitely going to be our faster reaction. In the office hour question, I went through and did the whole reaction coordinate diagram up to this point. You should check that out. And oh, this is interesting. This one has 3 resonance structures, right? So you might think, oh, 3 resonance structures versus this guy would have 5 resonance structures. Only 3 resonance structures, that shouldn't be as stable. But it's aromatic, it's way more stable. This one can have 5 resonance structures. It's not as stable because it can be anti-aromatic. I think what this one does to avoid being anti-aromatic is it stretches out its bonds so that there's not like overlap around the ring. So it's not a true conjugated ring because this p orbital is not pi bonding much, it's further away. Now for a new reaction. We're ending off chapter 15 with these electrophilic aromatic substitution reactions, or EAS. I've spent most of this chapter talking about how aromatic rings are low in energy and they're very stable. That's true, and so if you wanted to have them be reactants and react with other molecules, you have to take this very stable aromatic compound and react it with something that's very high energy and super strong. So that's the overall theme. We're going to learn, I think, 4 of these. Well, chlorination, bromination are pretty much the same. Nitration, sulfonation, Friedel-Crafts, 6. But they're all going to be the same concept. You'll see with practice, they're not a problem. They're all going to involve first making a super electrophile. Because the aromatic ring is going to be acting as a nucleophile. and the aromatic ring as a nucleophile is super weak. It's not a strong nucleophile at all. It's stable, but if there's a super electrophile, something so strong that it has to react with it, it will. And so we have to make a super electrophile, and then we're going to lose aromaticity. So the aromatic low energy benzene ring is going to temporarily lose aromaticity, and then it's going to re-aromatize. All three of these will happen in all of these examples we're going to do. Okay, so let's try the first one. We'll do a bromination of a benzene ring. So in order to react this very stable benzene, you could try adding bromine. It doesn't react that much. But when you add a catalyst, iron 3 bromide, you can create a super electrophile here. And then when I think of it as a super electrophile, it's like our electrophile goes into the phone booth, gets on his Superman cape, and da-da-da-da, it's a super electrophile. So we're going to see that a lot. And what the product will be is you could brominate the ring like that. And you can produce HBr as well. And the catalyst remains the same. It doesn't change. Its catalyst gets regenerated. So it should seem strange that I said we made HBr, but we are in, because HBr is such a strong acid, but we are in extreme conditions here. This super electrophile is not your normal reaction conditions. It's very harsh. So that's what happens. And let's talk about the components of this. So the benzene ring is the nucleophile. These guys are going to make the super electrophile. And we're substituting a hydrogen. See how there was a hydrogen here, and now it's a bromine? So this is called an electrophilic, because we're using a super electrophile. Aromatic substitution. The aromatic ring is getting a hydrogen atom substituted for a bromine atom. Okay, so let's do the mechanism. First off, the bromine coordinates with the iron 3 bromide, or ferric bromide. I just show it simply like this. It's a classic Lewis base, Lewis acid, just one arrow. Okay, and then when you get to this point, we went from a bromine, which a bromine can be an electrophile. We've seen it been attacked by nucleophiles, so this is an electrophile. Just a regular old Clark Kent electrophile. When it interacts with the iron 3 bromide, it becomes the super electrophile. So now this super electrophile is strong enough to react with the very weak nucleophile benzene. Very, very weak. How does it react? It can, I'll make this bond a little different. One of the pi bonds is going to swing out and bond to the bromine on the end. It's going to go whoop, like that and break the bond. And this step maybe looks a little weird because the middle bromine has a plus charge on it. Why didn't I just add to the middle bromine? Well, if I add to the end bromine, I can get rid of that middle bromine's plus charge. That's just the way it seems to work. And we have to be very careful about this. I'm going to add this hydrogen. A lot of times students get mixed up at this point. We have to be careful. I'll show you what I mean. We have to draw this out in the following manner. I've got my bromine here that I just added. I still have that hydrogen, and now I have the iron with 4 bromines on it and a minus charge. And I've got my lone pairs and my bonds like that, and a carbocation here. So, as I said earlier, I needed to make a superelectrophile. Da, 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 da. I made the superelectrophile. Da, 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 da. I need you to say that every time, by the way. And then the superelectrophile reacts with the weak nucleophile benzene to lose aromaticity. So we lost aromaticity. Is this an aromatic ring anymore? sp2, 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 oh, sp3. So lost aromaticity. So this is a very high energy intermediate. But it happens because the superelectrophile can make things happen, right? It can fly. And I also want to point out the resonance for this guy. It's going to play, the resonance for this intermediate is going to be a big part of chapter 16, the biggest part of it. So let's practice on that. So even though this is an aromatic, it does have some resonance. I can put a hinge there, swing this pi bond here. And once again, I got more resonance. That pi bond can swing down there. All right, there we go. And that's it for the resonance for this one. And then we have one more step, re-aromatize. Now, how's that going to happen? We need to lose this hydrogen, right? That's the substitution, a hydrogen substituted for bromine. We also see HBr as a product. So the way I want you to draw that mechanism is you're going to take the bond between the bromine and the iron. Imagine that bond is hinging on the bromine. It's leaving the iron. And it's going to deprotonate here, which you can see, boom, can re-aromatize like that, make the bond to the carbocation. And we get our final product. And HBr. And our catalyst is regenerated. So, make the superelectrophile, bum, ba, da, da, react to lose aromaticity, has some resonance, and then re-aromatize. And hopefully you're thinking, wow, bromine is one of the world's weakest bases. Why would it deprotonate this? The reason why is because it's going to create this low energy aromatic compound, and these are just really extreme conditions that we're running this reaction in. This reaction will also work with chlorine. You should practice drawing out this one. So it's just the same thing. You're just changing the letter B, R. The letters B, R for Cl. First step's the same. I'll do the first step just to get you started, and then you can finish it off. So you have your chlorines and electrophile, but not that strong. And then what it adds here to the iron, dun, da, da, da. You get a superelectrophile. The benzene can open up, add the chlorine on the end to it, lose aromaticity, re-aromatize. Next up, nitration. So if you take benzene and you react it with nitric acid, one of the very strong acids. And then add sulfuric acid, an even stronger acid. Two of our strongest acids. You mix those up, and they can make a super electrophile that will react with this very unreactive benzene. And you'll wind up making nitrobenzene. Which has an interesting structure. It's got a bond to the nitrogen, and then actually has resonance. It's a 1.5 bond to the 2 oxygens. I'll show that this time. See, it's got resonance through the nitro group, resonance in the benzene ring as well. I didn't show that resonance there, but yeah, nitro groups, we're going to see a lot of this. They're an interesting one in that the nitrogen always has that positive charge on it. It's very electronegative, so it withdraws electron density from the ring a lot. That's going to play a big part in things we're going to see shortly. So let's do this mechanism. We start off with our nitric acid, and our sulfuric acid. Turns out sulfuric acid is a stronger acid than nitric acid. They're both considered strong acids, but sulfuric is a little bit stronger. At least in these conditions it appears to be. So the sulfuric acid is going to protonate the nitrogen. So what do you think it would want to protonate? Would it want to protonate this O minus, this O with no charge? That's actually not right. They're both -0.5. So does it want to protonate one of those -0.5 oxygens? Or this one without a charge? Well, it can protonate both, but if it protonates one of these, it's a dead end. I'll show you what I mean. I won't show the curved arrow mechanism for it, but if it protonates one of those oxygens, so you get this, there's not anything the molecule can do from that point. So it can happen and they can come back. It can happen, it can come back. So this is just a dead end. But if it protonates that OH oxygen, then things can happen. I'll show you. So if it protonates here, you get the following. And what does that protonated water there look like? Well, it looks like water, right? But what does that remind you of? Does it seem like something we've done a lot of? Kind of like we took an OH bad leaving group, made it a good leaving group, right? Yeah. So that's what's happening here. And at this point, that water can come off, and it can come off because there's a pair of electrons right here ready to push it off. So boom, and the oxygen's got a plus charge, so it's pulling the electrons to it. This is another example of a push-pull mechanism. I think we mentioned a little bit. I think it was in lab, in a pre-lab. We're going to see this a lot. This is a push-pull step. So this arrow right here, think of as it's pushing off the leaving group. And then this oxygen is pulling electrons towards it. Whenever you have an atom with a good leaving group and another atom attached to it with a lone pair, it can have a push-pull mechanism like this. Okay, and you know what just happened? Dun, 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 dun. We made our super electrophile. This is a very strong electrophile, so strong that it can react with even the weak benzene. And how does that happen? Just like we saw with the bromination and chlorination. Pi bond can swing open, and I suggest you do this. On your hinge, put your hydrogen. A lot of students get confused about which hydrogen to deprotonate later, but if we have it drawn now, you might not. And then one of these pi bonds has got to break to the oxygen, so we get that. And something students forget a lot is the plus charge on the nitrogen as well. So don't forget there's like a plus charge on the nitrogen. Pretty much this whole mechanism, it's always got a plus charge. Now what did we do? Which step did we do? We first made the super electrophile. We just lost aromaticity. And even though we lost aromaticity, it can be stabilized a little bit with resonance, right? Yeah. We can see that pi bond swinging that way. And then I'm going to show you an abbreviation of this. You can abbreviate it as NO2 now that it's... I want to see it this way when it first reacts, but now I can put NO2 there, nitro, because it's got a plus and a minus. It's overall not charged. Okay, and then it's got another resonance structure. So yep, it's got 3 resonance structures just like the bromination and the chlorination did. And now we need to do our last step. We need to re-aromatize. So we need a base to deprotonate this just like we had before. And what kind of bases do we have in here? We don't have many bases. We do have more nitric acid actually, so it could be that. Or it could be sulfuric acid, which is, or not sulfuric acid, hydrogen sulfate. Which is crazy, right? Because this is one of the world's weakest bases, since that's one of the world's strongest acids. But traditionally, you see it drawn up as a hydrogen sulfate. It's going to deprotonate it. And something I didn't point out last time, I can deprotonate any of these resonance structures. It could be this one, or this one. So which one do you want me to deprotonate? Molly, which one? Do we have a Molly this semester? Oh my God, that'd be bad if we didn't. If we did. Molly was last semester. Yeah. What am I thinking of? I forgot you guys already. Sorry. It's been too long. Just kidding. Okay, let's go. Someone I don't usually pick. I pick everybody though. Tiffany, which one do you want to pick? Left, right, middle? Okay, I'll go middle. So hydrogen sulfate can deprotonate this. And I can have it go like this. I'll have the pi bond go there, hinge here, come down here. I'll erase that resonance arrow from earlier. And that gets me to my final product, nitrobenzene. And I've regenerated the sulfuric acid. Next up, sulfonations. So for this one, we start with benzene again. And we're going to make a sulfonic acid. Similar to our tosic acid. Tosic acid has a methyl toluene from toluene. This is a sulfonic acid. And how do we do this? So we're going to use sulfuric acid again. But instead of adding nitric acid like in nitrations, we use what's called fuming sulfuric acid. It has SO3 gas in it. So you've heard of concentrated sulfuric acid. So a step above concentrated sulfuric acid even is fuming sulfuric acid because it has this SO3 gas fuming out of it. It's super strong. When you order it, you get it in a bottle, a small bottle that has like a plastic coating around the bottle to make it less breakable. And then they put it in this packaging for vermiculite stuff and an aluminum can and then packing in a box. And then when they ship it to you, I believe they can only do it over the ground. They won't put it in an airplane. It's a little too dangerous. Same goes for like organolithiums and things like that. When you buy them, you have to buy them ahead because they won't put it in an airplane. It's too dangerous. So this stuff's crazy, fuming sulfuric acid, but you need that because benzene's so unreactive because it's aromatic. So let's start this reaction off. The fuming sulfuric acid can actually react with the SO3 gas can react with benzene just directly, but I like to show the mechanism this way. It kind of goes better with the theme, and this I think happens as well. So the SO3 gas, so here we go, boom. This is real high energy stuff. Got to do this in the fume hood, put your goggles on, put your lab coat on, and then have your undergrad do it for you while you go get coffee. Just kidding. It's not too bad. Just gotta be careful. Okay, here we go. So what we just did there was made a dun-da-da-da super electrophile. And now our benzene's ready to come in. And react with that. I'll pick a different pi bond this time. It doesn't matter which one. Does that make sense? And I will get, yeah, this one's reversible, I think. And you'll see at this point, we've already got our sulfonic acid on there. And we lost aromaticity, and this though has some resonance to stabilize it. I'll let you practice drawing that. It's the same resonance you saw before. So fill in the resonance. Pause the video, draw the other two resonance structures. And now I just need to re-aromatize. So what do you think is going to happen? Who's going to re-aromatize this? What's the base? I need to deprotonate that hydrogen. The carbon that gained the sulfonic acid has to lose a hydrogen. So you probably guessed right. It's crazy, I know, but it's the hydrogen sulfate has to come in and deprotonate that to re-aromatize. Oh, I did that wrong. And I can abbreviate this too. We see this abbreviated a lot too. SO3. I don't like it like that though. SO3H. And I did recreate the hydrogens, the sulfuric acid, so I'll draw that out. I definitely want to see the part of the sulfuric acid that changed. The rest of this I could have abbreviated. Okay, there we go. So there it is, we sulfonated the benzene. Something that's really interesting about this one is this is one of the, this is an interesting one that the sulfonic acid, once it's formed, it can be reversed. You can put it on and take it off. we'll look at that later. Let me just finish up all the forward putting things on the benzene ring. Now for Friedel-Crafts alkylation. This one involves making a carbon-carbon bond. So that's nice. You can do it with, we usually use chloride, sorry. You can do this reaction with secondary chlorides, primary methyl, and tertiary. And this is a good electrophile, right? Not good enough. We need to add a catalyst to make it a dun-da-da-da, super electrophile. So when I react this with benzene, I'm going to get the following. And HCl gas. So the chloride, you can see already, is going to be a base, which is weird, but it's a stronger base than hydrogen sulfate, so we've already gone crazy. Let's keep going. All right, let's do the mechanism. So we start off with our chloride, our secondary electrophile. Is that a strong electrophile? It's a pretty good electrophile. I'd say it's a good. It's not super strong, but it's a good electrophile. Secondary. And the aluminum chloride comes along, and it does pretty much the same thing you saw with the iron 3 chloride. It just comes in, it does a Lewis base, Lewis acid step, it binds to it. And it creates this intermediate, which is dun-da-da-da, the super electrophile again. So it got a lot more electrophilic. Since this is secondary, the chloride can actually just come off at this point. But you can draw the mechanism either way. It can come off right now, or it can stay on. I'm going to let it stay on. And then we need to have the nucleophile, the weak nucleophile benzene, come in and add to this. I'll do it like, I'll do it from this one, do something a little different. Boom, 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 boom. You can add in like that. And so we lose aromaticity. And now, but I made a carbon-carbon bond. Like that, right? Lost aromaticity, and it has resonance though to help stabilize it. It'll have 2 resonance structures. Practice drawing those out. And so we made our super electrophile, dun, da, da, da. Lost aromaticity. How are we going to regain aromaticity? We're going to use this guy. To get to our final product. And regenerate our catalyst and make HCl. Not too bad, right? Same pattern. Super electrophile, lose aromaticity, got some resonance to stabilize a little bit, re-aromatize. Okay, one last one. Last we have Friedel-Crafts alkylations, or sometimes it's referred to as acylations. This one's going to make ketones for us. So I can have, you need an acid chloride, and I can have any number of carbons there. I need at least 2 carbons. Can't have a hydrogen here, it doesn't work. But you can have 3 carbons, 4, 5, whatever. And then this is a strong, pretty strong electrophile. These guys are called acid chlorides. We'll be seeing a lot of those. But they still can use some help, and we add again the aluminum chloride, like the Friedel-Crafts alkylations. And what you wind up with is a ketone. And you make HCl. Cl as well. And so if I number my carbons, I can see I got 1, 2, 3 carbons there. 1, 2, 3 carbons there. So let's do the mechanism. Starts off interestingly like this. I'll show you something. Actually, yeah, I'll show you the two. So when this electrophile is becoming a super electrophile, it has two areas that it can bind with the aluminum. One area would be from the carbonyl. And I think that actually happens more than the chlorine. Because when this happens, it can have a little bit of resonance. So it can be stabilized by resonance. So this happens a lot, but even though it's happening, it's reversible, and it turns out this is a dead end. The mechanism can't go any further than this. So like this can happen, nothing else happens, it goes back. It happens, nothing happens, it goes back and forth. But then every once in a while, the aluminum will collide with the chlorine. The aluminum, the chloride of this, and when it does, it can proceed to become a super electrophile. Dun, 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 dun. Okay, and that's the super electrophile. Well, actually, it's kind of the super electrophile. But we're going to do one other thing to make it even better. Oh, and I want to state in general, when you have a situation like this, I've stated this before. If you have a molecule like this, where there's a double bond to one atom with a lone pair, single bond to the other atom with a lone pair, this atom is usually more nucleophilic than that one, because when you react and add something there, there's resonance. So that's why I wanted to point out, oh yeah, this happens, it's going back and forth, this goes back and forth. But when this happens, now we can carry on the reaction. How does that happen? It goes like this. The lone pair on the oxygen could push down, and the chlorine with this plus charge can pull away. It's another push-pull mechanism, huh? And now I'm going to say this is our reacting super electrophile. Dun, 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 dun. Yeah, it's kind of sad. Usually I make a joke of this with the whole class, and I have people, I assign them to be the dented and outers, but there's nobody to dent it and out here. We got our super electrophile, and our benzene comes in. And it can have right there. We're going to lose aromaticity though, but we can regain it. Lost aromaticity. We do have, let me count my carbons here. We got 1, 2, 3 carbons, 1, 2, 3 carbons there. And we'll have resonance, draw out the resonance, practice that. You're going to see it's super important for chapter 16. We're going to re-aromatize, and I bet you can already see it. There we go. We got it. Catalyst is regenerated. And so you've learned a lot of new reactions here. You learned how to brominate a benzene ring. You learned how to chlorinate a benzene ring, nitrate, sulfonate, alkylate, and alkanylate, acylate. So that's it. Brominate, chlorinate, sulfonate, nitrate. I think we just did 6. So, but it's not hard to remember because when you're practicing one, it's making you better at the others too because it's all the same kind of pattern. So the best thing you can do for yourself now is to try practice drawing these out a couple times each till you're like sick of it. And then when I get to chapter 16, it'll make a lot of sense because it's just going to be building off of this stuff. Okay, I think that's enough for now. I think 1:11 is a good stop time.